Good afternoon. Thanks very much for coming to this session. My name is David Goon. I'm a consultant based in the UK. For those of you who came to my session yesterday, I'm happy to see you back in the crowd. For those of you new, I'm actually based in the UK working with customers such as yourself in order to provide information and best practice advice to the development of Windows mobile applications. So one of the areas that tends not to be discussed in the early stages of any application development phase is what about performance? What is the actual required performance of an application? Now, requirements are one thing, and of course trying to meet those requirements are a whole different ballgame. In this session, we are going to look at the tools available to you that you can use in order to determine how performant your application is, given the requirements you've been set. This session is going to be an hour and 15 minutes long. I'm hoping to leave a bit of time at the end to answer any questions you may have. But if that is not possible, I'm happy to take questions outside the room because I think I'm going to get kicked out right on the bell. But I'll be happy to hang around outside to take any additional questions. So before we get started, I want to go through the goals of this session. So obviously it is to discuss how you would actually improve performance and how you monitor performance on Windows mobile devices. If you work with the compact framework, this session is going to be relevant to you. Unfortunately, I'm not going to have enough time to get into native tools that would measure performance for C, C++ type applications. We won't be looking at specific technology performance optimizations like SQL Server Compact Edition. And basically, I'm assuming that you are familiar with the .NET framework kind of programming model and that you're familiar with the compact framework requirements as well. So let's get started. So today, what we're going to go through is talk about performance in general, in terms of the business requirements for performance. We'll then look at a few preconceptions about performance on the .NET Compact framework, and hopefully we'll dispel those. We'll then look at performance at various stages of application development. So the first area is right up front at the design stage. Design decisions made up front has a huge impact on your performance characteristics at deployment. So if you can avoid major mistakes up front, you will have less of a struggle to meet your performance targets at the end. We'll then look at the tools available for both performance in development and performance at runtime. Okay. Now, the examples that I'm going to show you is going to be an exercise in the bleeding obvious today. Basically, in 75 minutes, it's going to be hard to show you the nuances of trying to determine where performance bottlenecks are. It requires, obviously, a full understanding of the system being tested, and of course, it requires some experience in seeing common performance problems. So hopefully you bear with me. The demos are going to be a bit contrived, but the idea is to show you how the tools can extract relevant information out versus trying to debug a real-world performance issue. So how fast is fast? It's a strange world we live in. If you work for, I don't know, 2 months on improving the performance of an application till you think, you know, this is really great, it's snappy, it's responsive, etc. You ship it to your users and they say, it's okay. That's all. However, if you don't do a good job of it, and you know there's a lag time, the users start complaining, I can't use this. This is not going to make my day productive, etc. So in this world, having acceptable performance is expected. However, low performance is unacceptable. So we must always be working against that sort of limitation. But what is good performance? So performance means different things to different people. A lot of it are common attributes like, it should be responsive, etc. But seriously, I mean, for a particular application, it may have a whole different set of performance criteria based on another one. So for example, an application that takes some data every day, processes it, and then sends it somewhere else, for that performance, it may require more towards the reliability and scalability of being able to handle that versus the actual speed of processing, so long as it keeps up with the volume. However, an interactive GUI-based application, a lot of the performance criteria is going to be based on how responsive it is, how much work the user can get done while they are actually using the device. Now, we have a scalability lab in the UK, and we have customers that come in for performance testing. And this is not mobile devices, it's actually for server applications, web services, rich clients. One of the key questions we ask them before they come in is, what are your performance targets? And this is usually an interesting question to have, because the requirement usually on the design document is, it must perform well. But what does that mean? You can't work towards a specification like that. You have to think about specific targets. What's the response time? What sort of data loads are we talking about? How many users? How many devices? What sort of backend configuration? Are we working against a server farm? Are we working against just a single machine? This has to be laid out before you can actually test for performance in a reasonable way. The next thing is, of course, to have performance as a key element of your development. So you can't leave performance as an end test, a QA, just before release. Performance problems found during that time is probably going to be extremely hard to get rid of, and it's going to be very, very expensive. So if you're continually testing for performance issues throughout, keeping to the requirements set by the end customer, then you're going to find that you're going to be able to identify performance issues early, and you're going to be able to fix them before they become a huge issue. So from experience, a subsystem at the very early stages of development, excuse me, will be probably fairly fast in performing. However, excuse me, as the features get added to the system, additional logic needs to run, and performance obviously slows down at that point. So I'm going to start this off with a fairly basic example of performance in a user application and how it's perceived. Now, we'll go through the code later, but effectively what this application does is simply loads in an article that I pulled off MSDN, and you can see there's quite a lot of text in it, display into a text box on the UI of the application. Now, imagine that this is actually extracting this data over the air or down the network wire in order to load into the application. So you got a large amount of data that you need to get into the application, and we'll have a look at this running. While that is actually loading up, obviously this is assuming that the data is going to come over the wire. When determining your test limits, or rather your test targets, that is another area that is usually overlooked. When discussing with your end customer as to what good performance means, they usually say an end-to-end response time of 20 milliseconds. Okay, you might be able to do that if you control every stage of the solution. But if you're using anything like wide area networks or systems that are not under your control, then you have to put that into consideration in the overall test plan as well. All right. Okay, when this loads up, you should see a fairly simple UI. It's simply a text box where you can type stuff in. And there's a menu here that pops up with certain options that we will use later. When I hit the load button, it's going to try and suck in that that article and display it into the text box. Sure, I hit that. There we go. Now the thing though is while it's loading in, the UI now has been frozen. So this is a fairly common issue when you actually use the primary thread in the application to do any sort of processing. You can see now that it's become responsive again. At least in this application, you have some feedback to the user in the form of the progress bar. However, a common problem that comes up in performance testing is, at first, you use the UI thread for a fairly simple operation. But as time goes on, you add more and more work to that UI thread while it's actually processing some event from the user. Eventually, it starts bogging down the system. Also, there are considerations like it may be very performant if I'm downloading a fairly small article. But what if the user selects a fairly large article? An unresponsive UI in that situation then becomes unacceptable. Okay, let's look at the code then. In this case, the solution is obvious. We need this work to be done off the UI thread, which means we need to actually have a separate thread to do the work in the background. Now, this is the application that you just saw. We have the text box text cleared first, and then we create an article object, which is just the encapsulation of loading of that file. And as the article is loaded, we have a load progress event handler that is then used to call the load progress code in order to update the progress bar. Now, this is the important bit. If the single menu item, which is over here, so under threading, single, if that is checked, then we load the article on the UI thread. If the multi-threading item is checked, we then use this API called queueUserWorkItem in order to launch a background thread. This starts a thread in the background, or rather queues one off the thread pool in the background in order to actually do the loading work. We provided the function to actually execute, which it does, and that does the exact same load article call, except that it's now on a separate thread. Now, the last bit I want to show you here before we go on is the load progress event handler. So since we got two different threads actually loading the article, in one case the UI thread, in another case a background thread, you can only update UI elements with a UI thread. So we have to check to make sure that if we are on a background thread, when the progress bar needs to be updated, that we actually call invoke in order to make sure that the UI thread is used to update the progress bar. Okay, so now obviously if we then set threading to multi and we do another load, the UI is still responsive while the application loads the data. So a fairly simple demonstration of how you can increase the perception that the application is performing better simply by using a background thread to do long-term processing. There we go. So what affects performance? As I said earlier, solutions must of course be correct. If you have the fastest application in the market, but only gives you the right answer, one time out of 3, it's not going to be worth much. However, there are certain common criteria to add to the correctness of the application. Generally, when a user is interacting with the application, it should respond fairly quickly. I don't know if you have the same experience with me with set-top boxes, but I find it very distracting when I try to change a channel and it takes about 1.5 to 2 seconds before the channel actually changes. If you are channel surfing, you want to be able to flip channels really quickly. And some set-top boxes are better at that than others. So it has to be responsive. Of course, when the application has work to do, it should do it as efficiently and quickly as possible, and it should stay up. The worst impact to a user is to have an application fall over every once in a while. We should talk, right? But especially in the Windows Mobile arena, where these applications are supposed to be running on a long-term basis, you definitely need to have reliability as a key consideration. So where would performance normally get hit the worst? Assembly load time is the first one that I want to talk about. So if you have a large implementation and it's monolithic, there's a huge exe that you need to load in. That image needs to be loaded into memory before it can be executed. So that's going to provide a delay at application startup. Or if you are actually loading a particularly large library, there's going to be a delay when that library actually loads. After the library or the exe loads, in order for it to execute, of course, the just-in-time compiler needs to kick in and convert the intermediate language into actual binary on the CPU to execute. That, again, is going to introduce a delay. Finally, because of the way that the .NET framework handles garbage collection, as in the desktop, you're going to see delays occur if a lot of garbage in the application needs to be collected all the time. So these are areas where you can look at, and we're going to look at these areas later in order to determine what can be done about them, in order to sort of speed up the execution of the application. So let's look at a few myths before we get into that. So we have touched on a few areas where it says that, okay, there will be some delays in some areas. However, the runtime itself does not get in the way of actual execution. Since most of us are familiar with the .NET framework, we know that the just-in-time compiler actually generates native binary code to execute on the platform CPU. So once the JIT runs, the final code that actually executes at 100% of the CPU's capability. There is no translation layer in between. The other myth is that because we have the framework runtime, we don't need to worry at all about memory management anymore. I mean, that's what we keep telling people in the sort of marketing material, that, you know, the runtime's great, it's going to take care of all your memory problems. But seriously, you still have to look into certain areas where memory is actually an issue. So there will still be areas where you need to clean up, especially if you have things like unmanaged handles. So while the runtime is good at collecting managed objects, if your objects are holding handles to unmanaged resources, like GDI brushes, etc., if those aren't cleaned up properly by your application, they are going to leak, and that's going to cause an issue in your application. So we have this concept called finalizers that are supposed to actually take care of that. So finalizers in the .NET framework, generally, a lot of people equate them to C++ destructors. That is, when the object goes out of scope, your cleanup code runs, and that cleans everything up. So in the previous example of the GDI brush handle, you would then have a call to destroy object, the destroy object API or release or whatever, in the finalizer of that particular class. The thing, though, is finalizers in the .NET framework don't actually get called in a deterministic way. So they could be hanging around for minutes, they could be hanging around for up to hours. So you have to be really careful about when an object goes out of scope. So assuming we extend the example of the GDI brush handles, assuming your application continuously grabs GDI brushes, it creates new brushes every time it needs to do its work. It will create these brushes, and the handles will not be released. So long as there's no memory pressure, the garbage collector might not actually do a collection or run its finalizer. You could potentially run out of brushes before the resource is actually collected, released back into the common pool. Finally, a lot of people look at the garbage collector and basically say, well, why wait then? If finalizers are non-deterministic, I'm going to call GC collect. Now, the trouble with this is the GC in the framework is finely tuned to the operation of the entire system. So if you're calling GC collect every once in a while, you could potentially be running collections when they are not required. And this is actually going to impact your performance more than if you let the system actually work with it. So a few differences between the compact framework and the desktop framework. First of all, in the compact framework, garbage collection happens on code pages as well. So code gets pitched if there's a memory pressure issue. So that means that the just-in-time compilation step needs to rerun really quickly as and when those code pages are needed again. Now, because of that, the compact framework is optimized to actually compile code very quickly at the expense of fully optimized code at execution time. So they trade code execution speed for speed of compilation. The desktop framework does the opposite. They favor fully optimized code versus the speed of compilation. Obviously, because the desktop framework doesn't throw away code. Additionally, when you actually go through a GC collection, the compact framework doesn't have a concept of generations. Any collection is a full collection. It goes through the entire tree of references in order to figure out what needs to be thrown away and what needs to be retained. So that's why it is a fairly heavy operation. And calling GC collect is probably not a very good idea. Okay, so in this stage, we are going to talk about how you can actually start improving performance in the application from the outset. So in performance and design, especially if you're coming from the desktop world, and you're in this room looking for tips as to how you can make great Windows mobile applications, you have to acknowledge that these devices are actually smaller. We don't have CPUs that run at the same speeds. We don't have as much memory. In fact, the memory model is very different. Rather than having 4 gigs of address space with 2 gigs for you to play with, we have effectively a 32 megabyte slot for your application and a further 32 megabytes for system DLLs. So that's a very much restricted area for your application to be working in. So when you're approaching mobile development, you've got to think about mobilizing aspects of your application that make sense on a mobile device. The worst decision to make is to take an existing desktop application and porting it wholesale on the mobile device. So if you have like an application with 30 to 40 forms on the desktop, that's not going to work very well on a Pocket PC, not with hundreds of controls, tabs, etc. The approach is to look at what the application actually does and to mobilize that small aspect that makes sense to be on the road. Now, management reports on a mobile device might sound like a great idea, but is that really necessary? However, things like data collection out in the field, that is one of the key mobile applications. It saves paper, and effectively what you're doing is all you need is an application to fill in a few data fields and upload that to the server. That becomes a more manageable application versus having a full ERP system on the device itself. So the first step in actually working with mobile devices is to think about the application itself, how it's going to be used, how long is it going to be used for, and what sort of work the users will be actually doing on it. The key decision here is that I've gone through with speaking to customers is, first, is your environment going to be mainly connected or is it going to be mainly disconnected? Do we assume network connectivity to be there or not? And that affects how you actually work with the data. And we'll go through a couple of scenarios later. So obviously, in a Wi-Fi warehouse environment, you can assume network connectivity to be almost present all the time. Okay, there will be black spots, etc., and that needs to be taken into account. But most of the time, you can rely on the network connectivity. However, if you are relying on GPRS connectivity for a field agent that needs to go out into the countryside, then you're going to have to start thinking about performance issues when the coverage doesn't actually extend to where that person is. So a part of that is to figure out whether you want to have data-centric, which is using replication on databases, or a service-centric application, which requires connections to a back-end server in order to get its work done. So here's an example. Field data collection, when a person actually goes out and starts collecting data, maybe for surveys, maybe it's a stock take, etc., within retail areas, we would expect that this person would get his work orders and need to actually have those orders with him during the day. Hence, he's going to need some local data storage. Now, the way most field workers work is they get a list of tasks they need to do at the beginning of the day. They then spend the day doing the tasks, and then at the end of the day, they update the backend server with whatever they have done. That means that we can actually think about a data-centric approach. We can have remote data access from SQL Server Compact Edition, which is basically a pull technology, so that you can have quick lists, lookup tables, etc., down onto the device as quickly as possible without tracking any changes. And you can have merge replication for those records that you actually need to make updates to for later upload back to the server. So at the end of the day, you would then update with whatever the field data collector has actually captured back on the server. And this makes a lot of sense. What about mobile banking? Here we have a whole different usage scenario. Here we want to have responsiveness in terms of moving, say, funds from one account to another. You don't want to wait for an hour later to actually see the results of what you've made a request for. You want to see that an acknowledgement is received and that you can actually see the funds in your new account immediately. So you can imagine if we actually swap the decision of the technology. Imagine that the field data collector has a web service sort of transport implemented. They will be extremely frustrated. Whenever they're out of coverage, they can't get any work done. Because so long as you don't have connections back to the server, the app can't perform. Similarly, in mobile banking, if you use the data-centric approach, that would be extremely frustrating as well. Having to do a merge replication synchronization for every task that the user actually executes. So you can see from a design standpoint, you want to pick the right technology right at the beginning in order to get the performance capabilities that you're expecting for the application. Finally, in the web service case, we do want to make sure that you can scale. So keep the web services as stateless as possible. So quick performance wins. Earlier, we talked about key performance influences. The first one was assembly load time. So try and code, less is more effectively for mobile devices. Rather than having huge amounts of functionality, think about key functionality that would be most useful on mobile device. The smaller your end assembly is, the better it is. It's going to load quicker, it's going to be easier on the memory footprint, etc. A lot of people ask, what about NGen? Why don't we actually supply NGen assemblies? The reason is, IL is actually more compact than any native CPU binary. So if we actually supply NGen binaries, the footprint of the framework is going to be huge. The other way is to actually lazy load your assemblies as you need them. So your EXE may actually be fairly small, loads first, the user gets a response of the application running, and then you can then lazy load additional libraries as and when you require them. You've seen the second point already demonstrated earlier. So in the bad app, the UI thread was tied up while loading the document. So don't tie it up. Use a background thread to do long-term processing. In order to get over the issues with the finalizer, issues with keeping resources in memory for longer than required, such as the manage handles, implement the dispose pattern. And as developers, if the rule of thumb should be, if an object exposes a dispose pattern, a dispose interface, we should call it. So we should call it when we are done with the object, as a rule. Now in mobile applications, these applications tend to run for a long time. Effectively, they're 24/7 on mobile devices. So you might want to start thinking about perhaps keeping objects in memory rather than recreating them all the time. Benefits I've seen from this approach, especially in memory-intensive applications, is that you then have a set working size that is stable. Obviously, if you have a memory leak, there's a whole different story. but you then have a stable memory footprint that should be maintained for as long as the device is running. If you're constantly creating and destroying objects, the GC needs to kick in, etc., there is always a chance that the memory allocation might fail at some point. In platform invoke, this is where you're actually calling out to native APIs in order to get functionality not in the framework. There are ways that you can do this that will reduce the amount of marshalling that occurs across the boundary. So with each platform invoke call, all the arguments need to be serialized into a format that can be sent across the border. So that's the marshalling step into the native API, and the results need to be marshaled back into the managed world. So imagine if you had to make enormous amounts of these platform invoke calls. It might be a better idea to wrap all this in a C library and make all the native calls within that library and expose a very coarse C interface to your application. So rather than making, say, 15 platform invoke calls, you make one platform invoke call to a coarse C function that then makes a 15 calls that you need to have happen. So that's what we mean by a platform invoke wrapper. The next one is a classic. So string builder versus string. We all know strings are immutable in the .NET framework, and we are going to have demos after this that basically show you the effects of having strings versus string builder. So string builder provides you with the buffer, obviously, and work within that buffer doesn't create new strings to replace the strings that have been changed. So since strings are immutable, every time you do any concatenation, rather than the strings actually being joined together, two strings are thrown away, a new one is created with the two values. So the three layers here tend to be in the sense of these being the probably biggest hitters, this being the middle hitters, and the last three being, well, they will improve performance, but you might not see a lot of, you might not see a massive increase in it. So, but I'm going to explain why I put these here. So using generic objects versus object collections gets rid of a performance hit due to the boxing and unboxing of objects in .NET. So whenever you use the object reference versus a particular type itself, .NET basically takes a data type, especially if it's a primitive data type, and boxes it into an object in order to store it in a collection. The generic version, on the other hand, creates code to handle that particular primitive data type, so say an integer or a character, etc. So that way, there is no boxing or unboxing penalty when you use generic collections. And that's a little bit quicker. Simple properties. So in simple properties, if you keep your accessors for the properties fairly short, fairly simple, i.e. just returning a value, etc., the IL is going to actually inline code that calls those properties. So rather than having the full cost of almost a function call to a property accessor, the property value is actually inlined into the code. So it's that much faster. Finally, the .NET Compact framework, due to its compact size, doesn't actually build virtual tables for any of the classes. When you're actually using virtual function calls within the .NET Compact framework, it basically goes through the object's call table to find the method you're talking about. So there's no quick lookup through a V table. So if you have lots of objects with a lot of virtual functions in it, in order to do that nice polymorphism sort of thing, then you're going to actually be hitting a performance hump every time you make a virtual function call. Okay, that's a lot of talk. So finally, we get to the interesting side of the presentation, hopefully, where we can actually see things in action. So performance in development. So we have talked about all the principles about design, etc. We are now going to look at the tools that are available to you to actually start measuring performance. So we are going to assume that you've had your discussion with the customer, you have your performance targets that you need to hit. So how are we going to actually see how we can actually meet those performance targets? So the Visual Studio Profiler, which is the first tool I'm going to show you, is a great way to have a quick look into areas of the application that might be taking up the most amount of time, as in the desktop application world. The second sentence there might be interesting to a lot of people. It's not supported for smart devices, so why is it up here? Well, the thing is, if you are building a compact framework application in version 2, it is a true subset of the desktop framework. So any mobile application you build in the compact framework will run on the desktop framework. So there are certain caveats in doing that. Obviously, you can't have any device-specific code within your application if you want to do this. However, if you are able to stub out the device-specific code, then it becomes a very useful tool to get more information from your application where it would not have been possible before. Now, the two things to keep in mind is that obviously you are running your application in a different environment. The x86 processor that you're running on is going to be totally different from the ARM CPU on the device itself. However, if you take things like that into consideration, then you can at least see relative times as and when the performance becomes an issue. Okay. So let's go back to the application here and shut it down. What I'm going to do first, so I'm going to go to the developer menu item. Under profiler, I'm going to start a new performance session. Now, of course, since this is a demo, I've made sure that I haven't used any device-specific APIs. But if you do have any, then just stub them out so that they won't actually cause an exception. Within the targets, I'm going to add a target binary. And you will see that this is exactly, if I go back to here, go to Documents, I'm just showing you that this is actually, this is actually the actual project that I'm going to debug. So perf test, bin debug perf test exe. So this is the exact same binary that would have been deployed on the device itself. So once that is done, we can simply launch the application with profiling. And it's asking me to upgrade my credentials because I didn't start Visual Studio as an administrator. We'll just say yes to that. And we should then see the application pop up. So this is a compact framework application that has been retargeted to run on the desktop. It has that load button, which was the left load button, and a menu with the trading and concatenation items as in the application on the Pocket PC. So I'm going to hit load a few times. Of course, it's going to be a lot faster on the desktop than on the Pocket PC. And I'm going to shut that down. So this is then going to generate a report that you can then drill into to find out where most of the time has been spent. So that's happening now. So the inclusive sample functions. So what happens with this profiler is basically taking a snapshot every X amount of intervals in order to figure out where the call stacks are, etc. By inclusive, it means that the IP, the instruction pointer, was actually within that method when the capture was taken. Exclusive means that the function was actually on the call stack when the capture was taken. So you can see that over here, most of these have to do with the runtime itself, so we won't actually look into that. But under the exclusive sample functions, we can see that the first entry is to a call to the white string copy, effectively. So let's drill down on that by double-clicking on it, and you can continuously drill down until we see that this is the sort of caller-callee view. So we can see here that it tells us that this string copy function has been called by the fill string checked function. And we can continue drilling into that. So it's called by the concat function twice. Finally, we actually get to our application itself, perftest.article.loadArticle with string. So here you've seen that by running it under the profiler, we've determined which function actually has spent the most time processing And from there, we have drilled down to which caller actually called that function. Okay. So that's a quick view of using a built-in tool in Visual Studio to get some performance data out. Next step is to actually have some better granularity. And you can roll your own profiling for those applications that you don't want to stub out various device requirements. So you have the stopwatch class provided under the diagnostics namespace that you can use to actually take timestamps. The thing that is, by itself, it probably isn't that useful. But I'm going to show you how you can actually leverage things like the trace class and the new unit test support in Visual Studio 2008 to actually combine this information to allow you to test for performance as part of your build process. Things to keep in mind in any sort of performance test. First, because of JIT and load times, your first run will always be slower than subsequent runs. Also, due to various different factors, always take a statistical average. So don't run just once and take that number. Make sure all your test runs tend to run a certain operation multiple times, and you take the average time that the operation took. Also consider dependencies. This goes back to my earlier statement about if you don't control the end-to-end response loop, then you could be impacted by factors outside your control. So if you have an asynchronous call somewhere in your pathway, that is going to contribute undeterministic length of time to the processing. So let's look at manual profiling. Now within the application, let's shut that down. I'm going to show you the article object earlier, which holds the load article call. So it's here. So remember from the earlier code, effectively when I click the load button, depending on whether it's single or multi, it will actually call the load article function that I've implemented here. Here I'm using the stopwatch object, which is actually declared up here. And you can see that it's part of the diagnostic namespace. And I'm basically resetting the stopwatch and starting it before I actually make the call with two different methods, which we will see later. The first one is to call it with a string object, and the next one is to use a string builder object. And we will see the performance improvement with it. So over here, once the operation is actually done, I'm going to stop the stopwatch and just trace out to the output window the amount of time it took to actually run that. So let's have a look. Deploy. Okay, so that's starting up. And once it runs, we are going to need the output window. Okay, that's up and running. So in the output window, view output, let's clear that. Let's run load a couple of times. So that's off. It's going and doing its thing. And this is using a string object. So string object needs all the concatenation to be happening, objects being thrown away, etc. You can see that. I hope that's big enough, but I can actually copy that into Notepad. So you can see that it took about 10 seconds on that run. So what we're going to do is we're going to run that again. Okay, so it's about 10 seconds overall. Let's copy that. Okay, so it's about 10 seconds. Okay, now we want to improve the performance of this. And since I'm using a string object right now, the idea is if I use a string builder, I'm going to be able to sort of make use of a buffer. I'm not throwing away objects so much, and I'm not actually causing as much stress on the garbage collector. The idea is that it would actually work a little bit better. So within the code itself, when you load the string, I'm simply taking a string and I'm doing concatenation on it. I then update the progress bar as and when the string is concatenated. Within string builder, I simply replace the string with a string builder object. The concatenation is using the append method, but the rest of the code is the same. So now I'm going to actually set it to use string builder, and we'll call load again. So this is all occurring on the UI thread. So we've removed that removed that difference from the test. So you can see that it's slightly faster, but it's not tremendously faster. So I would have expected to have much better savings than that. You're probably saving about between 1 to 1.5 seconds by switching the string builder. So there is another problem within this current application that we'll investigate in a little bit. Okay. Oops. There's one more part to that. Obviously, now that we can measure, sorry about this, that we can measure the actual performance itself, we can then make use of the unit test infrastructure within Visual Studio 2008 that now supports Windows mobile applications in order to build this sort of test limit into your testing suite. So if you have an end-of-day bill operation, so you have a daily bill, these tests can be run as part of that bill, and you can see if any changes made during the day actually impacts the performance of the application adversely to a point where it actually goes out of scope. It doesn't meet the targets set by the customer anymore. So I have a test project already created here. And effectively, I'm doing the same thing. I'm using a stopwatch. And I've written a test to use a call to load an article with the string builder. And I'm setting the assert statement, which will pass or fail the test, to a limit of 1 second. So if it's less than a second, then this test is going to pass. If it's more than 1 second, it's going to fail. Similarly, I've written another test with the string object. In the string sense, I'm actually giving it the same limit. So both operations should occur under 1 second. Now, you're probably thinking, but it took more than 8 seconds just now. So let's have a look. So if you go to test, and we run all tests in solution, oops, shut that down. Okay, so it should be starting up. Yeah, it's pending. And the tests are going to actually execute now. Okay, the first test, which is with string builder, is in progress, as you can see. And that's going to load in the proxy. And you can see that it's passed. So string builder actually executed in less than a second. However, with a string, it actually executes a little bit more than a second. But by this passing, it means that a lot of that time in the earlier trace, the 8 seconds to 10 seconds, is actually taken up by something else. And we are going to actually show you where that time is actually taken up. So in the code you saw earlier, we actually do an update on load progress for every concatenation that occurs. This actually goes into this event handler. And you can see that if we are calling an update to update that progress bar all the time, one call is going to be made for each and every letter that you actually concatenate onto the end document. So what I'm going to do now is I'm going to optimize this by basically providing a condition that basically says, only update the progress bar if the value has changed from the previous run. So if the progress bar is exactly at 80%, then don't do the update, don't call the UI in order to have that operation go. So let's run this and use the trace statements to see if that improves the performance any. Okay, deploy that. So with that little change, I'm going to shut that down. And we want the output window. Let's clear that. And this time, I'm going to load it. And you can see that the performance is much improved. So whether or not I actually use it with a string, so you can see it's cut down to about 3.5 seconds. Or if I use it with a string builder, you can see that it's about 2.5 seconds. So in this case, by using the tools and sort of building in the ability to monitor your application's performance, we have actually found an anomaly where the expected performance wasn't really as quick as what we thought it was going to be. And by looking into the code then, we can then identify areas which might not jump out at us from a cursory code inspection as to where performance bottlenecks might occur. Okay. Now, performance at runtime. So that's all while you're actually working on the application. You can actually build these things in. You can actually make the changes necessary to your application to get stuff running. What about after deployment? What about when the application is actually out with the user and they're complaining about performance issues? What's available to you then in order to actually determine what might be happening on the application? So since version 1.0 of the Compact Framework, you can actually enable performance counters, and they've added more and more counters as each version progressed. And you can enable these counters to collect a log file that will display a lot of information to you. To enable the log file, you need to set a registry setting in HKey local machine over here called perf monitor. You set the value counters equals to 1 to enable this. This will generate a text stat file, which with version 2 is isolated to each application that runs. With version 1 of the Compact Framework, all the counters are sort of merged into a single file, which might be hard if you're actually testing on a device with multiple Compact Framework applications running. With version 2, you can look for a particular application name. Tracking this at an overhead, it does actually slow the application down. So only use this if you really need to in order to help with your debugging. Okay, so this is the emulator I'm going to use. What we want to do is to go to the remote tools supplied by Visual Studio, and we want to actually enable the registry editor. We'll connect to the emulator, and this will show us the current registry hive on the device itself. Under HKey local machine, software, Microsoft, you will see the .NET Compact Framework link. It is under this link that you will need to add the key, perf monitor, and from there, you add a dword value called counters, and you turn it on. Once that is done, any application running on this device is going to generate that file. So let's start it up. Okay, and we'll do a few loads of the article so that we can actually get some statistics that are meaningful. We do it twice. And the stat file is actually generated only when you shut the application down. So we're going to turn it off. And we'll use another remote tool supplied by Visual Studio called the File Viewer in order to pull that file off. Okay, that's my application stat file that's been generated. I'll just throw it onto my desktop. And we can then pull that up. Oops. Turn off word wrap. So you can see it generates quite a lot of information here. Now, since throughout this session we've been working with strings and string builder, one of the key metrics that I want to show you is the amount of garbage collections that occur when you actually use string objects for multiple concatenations. So in this case, what we want to find is the garbage collections counter. And you can see within that 2 clicks of the load button, 292 garbage collections had occurred, triggered by the system itself. A total of 46,000 string objects had been created and disposed of. Okay, so that's if you have devices out in the field. This is a great way for you to get some information back in order to figure out what sort of major stuff is happening in the application as and when the performance issues occur. If you happen to have the device with you, or if you happen to have the application that, in a sort of development environment, you can actually connect that to the machine and actually debug it in real time. So real-time performance monitoring has been supplied prior with Service Pack 1 and 2 of the Compact Framework version 2, but it is now actually released as part of the Compact Framework Power Toys version 3.5 that you can download as a CTP. It will provide you up to the minute, well, up to the second data as to what the application is doing. There is some setup required, as you can see. You will need to copy some DLLs over to the device. And if the device is locked in any way, secured in any way, you will have to provision it to allow these DLLs to run. The application, of course, must exist on the device, and then you can get started and have some fun. So let's have a look at Remote Performance Monitor. So the other restriction that I failed to mention is that with Remote Performance Monitor, you actually need to have a physical device. It does not work with normal emulators. So this is the only time I'm going to actually plug in a physical device. So let's see if I can get this going. Okay, let's try that. Okay, so we are waiting for device center to spin up to say that we have a connection. And from here on in, we don't actually need the emulator anymore. So we'll just connect over ActiveSync, and then from here we can actually look at getting real-time data from my device here. So when you install the CTP for the Power Toys, you will find a program group here. Now you will want to run the Remote Performance Monitor as an administrator if you want graphical output, because you would want to publish the counters to Performance Monitor on the desktop. Start that up. Okay, so this is Remote Performance Monitor. In order to start the session up, what we want to do is to select the device. In this case, my device name Telparion under ActiveSync, and select the application. The first time you type in the application, subsequently they saved it. You can actually use a nice drop-down menu to select the application in question. So when I say OK, it's going to connect to my MDA over here, and we're going to see the counters start getting populated. Okay. Now, on the MDA itself, I'm going to actually do the same thing and load some, load the article. And you can see that the counters have been updated on the Remote Performance Monitor itself. So let's have a look at the garbage collections, 146 on a single run. I'm going to run load again, and you can see that that's climbing because I'm using string objects. Now, let's see how you can get graphical output out of this. So the first thing you need to do is under Options, start publishing to perfmon. We can then run perfmon, which will require administrator privileges. Okay. And under Performance Monitor, we'll just get rid of the current counter. And when you add counters, you'll see a whole bunch of netcf counters being added that you can select from. The one that we're interested in is the garbage collection one again. And basically, I want to find out the number of garbage collections that have occurred. It should be part. I'm going totally blind. There it is. We'll add that counter. We need to flip the scale down to something that will give us a better view of the value. And I'm going to click on the load button again. And as you can see, then you get the graphical output as to how your device is performing. So again, there's a whole bunch of counters that have been added, and you can actually monitor all this in order to get the performance metrics that you need. So let's do that again. Now, interestingly, obviously, let's keep that running. If we actually set it to use the string builder, and we hit load, you will see that no further garbage collections occur then. So you have already made a change that will reduce the amount of work that the system needs to do to keep running. So this is another example of how performance improvements can be detected and implemented. Okay. So that's remote performance monitor. All right. Let's see. That's monitoring in real time. And we'll shut that down. Okay, so the last section of this talk, I'm going to look at another major performance hitter, especially on long-running applications, which is memory leaks. So obviously, in a compact framework, we think that the runtime is going to take care of all of that. We're not going to see any memory leaks anymore. Not really true. There are certain situations you need to be careful about in order to make sure you don't have any memory leaks. So the idea is that the garbage collector basically looks from time to time, especially when an allocation occurs or a particularly large allocation is requested, to look for objects to collect. So stuff that has been released out of scope by your application, the garbage collector will go around and clean all this up. The thing though is, depending on how an object is referenced, potentially the garbage collector may find a reference that you are unaware of, which keeps an object in scope rather than out of scope. Those objects can't be collected. So three general areas are event handlers, and I'm going to show you a fairly typical scenario where you can leak event handlers. Static references within your project. So static references generally live for the duration of your project. They are located at startup. If you happen to have a static reference to an array that you add stuff to, and you don't clean that up, that's going to generally grow over the lifetime of your application. Finally, as I said before, in terms of the GDI brush object, you can leak native handles. And these need to be very carefully cleaned up, dispose method, etc., especially if you're working with COM objects. So within the Pocket Outlook object library, under the layers, we are still dealing with a COM library that interfaces with the device contacts, tasks, and calendar arrays. If you do not dispose of the Outlook session, then you could potentially leak COM references. So let's look at leaking event handlers particularly for this section of the talk. So here we have a shell. So the idea is this application is a shell. You will plug modules as and when required into the shell. So it's a fairly composable application, you could call it. So it exposes an interface because the shell wants to expose services that any module that attaches to it is going to want to use. One of this is an event that basically tells the module that the shell is being minimized by the user or sent into the background. So when this event occurs, the shell wants to fire a notification to the module. So it does so by defining the interface iShell. Now, a module that is developed for this shell generally then takes the shell in. The shell will actually create an instance of the module, and the module will then be initialized by the shell over here. So it sends its own reference in. The module then in the initializer basically makes an event handler, adds an event handler to the minimize event so that it can be called as and when any minimized events are fired by the shell. So you can see these are where all the references are going. Now the event handler itself then adds a reference over there. The module then is executed by the shell over here. And at the end of the execution, the module goes out of scope. This is a local variable. However, you can see that the event handler is keeping a reference to the module. And this is going to leak the module. If this occurs many times, you're dynamically loading modules like this, they're going to leak as the application runs. How do you fix this? Obviously, you need to remove the event handler. To do that, you implement the dispose pattern. So inherit the iDisposable interface, and within the dispose method, call dispose true. So an internal helper that will actually do the cleanup, and make sure you call gc suppress finalize so that the finalizer isn't called. I'll explain more about the finalizer later, but effectively, if you do not suppress the finalizer, the destructor of the class is still going to be called by the garbage collector, resulting in a performance hit. So this is the finalizer of the module, and it basically calls the same helper function, but provides it with a false Boolean value. So depending on whether it's disposing or not by the finalizer or by a direct call to the dispose method, it will then remove the event handler. This causes the event handler to be removed by the system, and then when the module goes out of scope, you then don't have the leak anymore. So let's have a look at that using Remote Performance Monitor. And the code I want to show you here is going to be in my leak test application, which I'm going to set as a startup project. And I've implemented exactly what I described just now. So we have a shell application here. So the iShell interface and the shell form inherits from iShell. And the shell interface basically exposes an event called minimize. When I actually run the application, all it does is it creates an instance of a generic module. You have to imagine that. Initializes the module and then executes it. We'll enable this dispose later to get rid of the memory leak. In the module, during the initialization, takes a reference to the shell and adds an event handler, shell minimize, to the event that's exposed. Okay. Now what I'm going to do is I'm going to start up Remote Performance Monitor again. Let's see. And this time, I am going to select a different application called Leak Test. So Leak Test is the application I just ran through the code with you. Let's start it up. I'm going to show you how you can see what objects have actually leaked. So here we have the performance monitor running. And before I do anything with the application, I'm going to take a snapshot of the heap. So we'll leave that for now. Now, in the device itself, I'm going to then click on run a few times, and that's loading the module in, making the references, and then getting rid of the module reference. But of course, we know the modules are leaking. Okay, now I'm going to take another snapshot of the GC heap. If you then use the view compare heap option, it will then tell you what you're leaking, or rather, Oh, sorry. Okay, thank you. It will then tell you, so I'll show you that again. So in one of the windows of the GC heat capture, if you do view, compare heat, you will actually see things that have been added to the heat since the last capture. So this is a great way to see new objects that have actually come into the heat. So here we can see that 3 new instances of module is now in the process phase. So in fact, we know that it's been leaked because we engineered the leak. Okay. And let's get rid of that one as well. Okay. Now what we're going to do is we're going to shut this down, and we're going to make that little change. So if we then implement the dispose method, what's going to happen is at the end, we're going to call dispose. It's going to call into dispose the helper function here. It's going to remove the event handler and then suppress the finalizer. So let's now build and deploy this. So, let's do this. And let's deploy it to the device. Okay. So the deploy has succeeded, and what I'm going to do is I'm going to start the application up again with the fixed version. And we'll do what we did just now. So first, I'm going to do a heat capture. I'm going to flip to the device and do 3 runs on it. So I won't flip the screen, just in case I forget to flip it back again. And I'm going to do a second heat capture. Now this time, when I actually compare the heat, you can see that the module item isn't there anymore. So we fixed the leak. So there are obviously other things you can look at right now, but as far as our application is concerned, the leak is no longer there. Okay. Right. Okay. Getting to the end now. So, new framework tools. Effectively, what we have with Compact Framework 3.5 is support for additional tools that will actually help with debugging stuff like memory leaks, etc. So the .NET CLR Profiler is one of the tools that is shipped with the PowerToys. And what I'm going to do is I'm going to show you the profiler really quickly, and then we'll look at the finalizer logging. So the profiler is a heat memory profiler. It does exactly more or less what we've done with the remote performance monitor. It detects stuff that is in memory, but it also shows you references back to the GC root. There is an API that you can actually use to actually control what the profiler does with an application as it's executing. Okay, do this really quickly. Let's shut all this down. And we'll start up the profiler. Let's get rid of that. Okay. So under the PowerToys, we have the CLR profiler. Now the CLR profiler is exactly the same way of using. We start an application, and I'm going to use the leak test based on my connected physical device. That's not going to work because I have actually fixed that application. So I'm going to need to break the application again in order to see any leaks. So let's do that. Okay. And we'll deploy that. Okay, so now we can actually start the CLR profiler. Okay. Right. So when the application is running, what I'm going to do is I'm going to show the current heap. And you can see that you get various graphical view of where objects are and what references are being held to each of them. So this is quite a complex display, and I'm not going to go into it right now due to time constraints. But what I want to do now is actually cause the leak to occur by just running the leak scenario about 3 times and show the heap again. One of the things that you can do with the heap is to show new objects. And this is a better way of looking at new objects that have been added to the heap. And of course, you get additional information as to where the references are coming from. Okay. Finally, we have finalizer logging. Now, in finalizer logging, effectively, objects that have not been disposed will finally have their destructors called. So in this case, we have a whole bunch of items here, and as they go out of scope, those without finalizers will be collected by the garbage collector immediately. But those objects with finalizers will actually get the objects added to a finalization queue, and a second run of the garbage collector is required to actually get rid of those objects. Now, if you're implementing a dispose pattern consistently, you will want to make sure that that dispose method is being called all the time. But how do you find out if somebody is actually letting an object go out of scope without calling dispose? The finalizer logger will actually do that for you. So this is the last demo. So if you bear with me. What we want to do is to actually make sure that the finalizer logging is enabled, and you do that using the PowerToy logging configuration. When that starts up, I can connect that to the physical device, and that will read the settings. So the finalizer is indeed enabled for the device. Now, rather than starting we need to start the app again. And what we'll do is start it manually. Actually, I'm going to do something to sort of speed it up a little bit. Because that was already pre-enabled, there is a chance that the file might already be generated on the device. So I'm going to see if that file already exists from the previous run when we actually ran the CLR profiler. So yes, so we have under program files, was where I put it. So there's a bunch of finalizer logs. I'll just download the lot of it. And put it on my desktop. And we can have a look at it. The leak test should be it. Now the reason why this finalizer log is empty is because I killed the last application, so it didn't get a chance to actually log its information. But luckily for perf test, the early application, I actually have managed to generate some logs for it. Now you can see that any object which doesn't have a dispose called will actually have its finalizer called, and this log basically tells you what objects have that condition. So this is a great log to have if you want to make sure that the dispose pattern that you've implemented is actually being followed. Okay, so in summary, hopefully this session has shown you that performance is really an aspect that you need to take into consideration right at the beginning of the project. And using the tools and technology that we've provided within Visual Studio, etc., with unit testing and all that, I hope I've demonstrated that you can actually implement performance testing as part of the build process, etc., so that you can actually make sure that you're continuously working towards the set performance targets that your customer is requesting. These are general resources for the day. I would like to ask that if you can, please do fill in your feedback. These sessions can only improve if you actually honestly feedback what you thought of it, whether it was useful or not. There is a chance for you to actually win a really cool device. And it says up there that it will close after 12 hours. So do please fill in the feedback as soon as you can. Otherwise, you will lose the chance to actually get another grab at that device. Okay, thanks very much for your attention.